Okay, let's unpack this. Picture your AI assistant, your digital agent, ready to tackle the chaos of the online world for you.
Right.
Maybe it's booking a complex trip across multiple sites, finding the absolute best deal on something specific by comparing specs and user reviews, or just, wrestling with a notoriously tricky online form.
Hmm.
The big question is, how do we make these agents truly capable, reliable, and, well, smart enough to handle all the dynamic, unpredictable stuff the real web throws at them?
It's a core challenge in AI right now. For a long time, the dominant approach to making AI smarter, especially at the point where it's actually doing a task that we call test time, has been about making it think more deeply before it acts.
Right, more internal processing, like
Right.
giving it extra time to generate a long chain of thought, a detailed internal monologue of reasoning
Yeah,
steps.
or maybe sampling multiple possible actions and
Yeah.
picking the best one based on some careful deliberation.
Exactly. It's all about deepening the intelligence within a single decision point.
Precisely. Trying to pre-compute or reason through every possibility internally before committing to an action. But what if the secret isn't just thinking more deeply before taking that single step, but actually taking more steps, interacting with the environment, trying things out, gathering new information along the way, perhaps even making mistakes and correcting them?
So moving from just scaling the thinking to scaling the doing, allowing the agent to act sequentially and let the intelligence kind of emerge from that interaction over time.
That's the fundamental question explored in the research paper we're diving into today.
Mhm.
It focuses specifically on web agents navigating in browsers and asks, what happens if we prioritize scaling test time interaction?
Okay. And our mission today is to really dig into this paper's findings, understand this potentially new, maybe powerful dimension of agent intelligence,
Mm.
and see why focusing on interaction might be a surprisingly efficient shortcut to being well-informed about the future of AI agents.
Sounds good. Let's maybe start by setting the scene a bit, looking at the challenge that these agents actually face.
Okay, so when we talk about AI agents operating in dynamic environments like browsing the web, it's fundamentally different from, say, a game like chess, where the rules are fixed, the whole board state is known.
Right. The web is messy.
Totally.
Yeah.
Every click, every scroll, every input can change everything. A pop-up might appear, a price might update, the page layout might shift.
Exactly. Agents need to operate under uncertainty and be able to adapt, in real time.
Mhm.
Current agents are often trained using methods like supervised fine-tuning or standard reinforcement learning.
Okay.
And they're typically optimized to pick the single best action at each specific moment based on what they can currently see.
And as we mentioned, the standard way to improve them at runtime has been that thinking more approach, chain of thought, or best event sampling.
Yeah.
It's like adding more layers of internal deliberation before the agent commits to pressing a button or typing text.
Yes, and the critical limitation of these methods really is that the thinking happens before the action. The agent is reasoning based only on the information it has right then.
Ah.
It doesn't get to take an action, see how the website reacts, receive new information, and then use that new information to refine its plan or figure out the next step.
Okay, so the paper proposes this alternative. Instead of just getting the agent to think longer per step, let's increase the number of interaction steps it's allowed to take during the task.
Yeah, more actions, more time in the environment.
That's the core idea of interaction scaling.
Exactly. Allowing the agent more steps means giving it more time and opportunity to actively engage with the website. It can acquire new information by clicking links, visiting different pages,
Mm-hmm.
explore different sections of a site, backtrack if it hits a dead end or makes an error, and dynamically adjust its strategy based on the feedback it gets from the site itself.
A great way to think about this, and I think this example comes from the paper, is booking a hotel.
Yeah, that's a good one.
An agent relying only on thinking more might analyze the first hotel listing it finds in incredible detail, right, using complex reasoning. But you, as a human, you wouldn't do that. You'd browse many listings, you'd click into different hotels, look at the photos, read reviews, check availability.
For sure. You gather the truly critical information through that sequence of actions. You interact.
Exactly. You can think perfectly about one hotel, but you can only find the best hotel by exploring others, which requires interaction.
And that's the key distinction here. Interaction scaling is about gathering new information through sequential actions in a dynamic world.
Yeah.
It's fundamentally different from just reasoning more deeply about the information you already possess in a static state.
Okay, so the researchers first wanted to test this, right? Just nudging an agent to interact more, even without specific training, could it make a difference?
Right. They did some simple experiments on WebArena tasks, which are these standardized simulations of web browsing activities.
How did they nudge it?
They used a pretty straightforward prompting technique. After the agent signaled it thought it was done with the task, they basically added a prompt asking it to pause and reconsider. Sort of like, hold on, take another look. Are you absolutely certain?
Just asking it to double check.
Pretty much. And what they found was quite telling, actually.
Yeah.
Simply prompting the agent to recheck like this increased the number of interaction steps it took to complete the task. And, importantly, this increase in steps led to a solid improvement in task success rates on WebArena.
Wow. Okay. So that supports the core idea more interaction can lead to better outcomes.
It definitely points in that direction.
Right.
But where it gets really interesting is when they compared this simple interaction scaling approach to those conventional thinking more methods, like forcing longer chain of thought or using best event sampling.
Under a fixed computational budget.
Exactly. Thinking about how much processing power, measured in tokens, they allow the agent to use per task attempt. They looked at success rate versus total tokens spent.
Okay, what did that show?
Well, the results were quite striking. The line on their graph, representing interaction scaling, where compute was used for more steps, showed a significantly steeper upward trend in success rate as the computational budget increased.
Steeper than the others.
Much steeper, yeah, compared to the lines for increasing chain of thought length or best event.
So for the same amount of processing power, distributing it across more actions led to a much higher chance of success than packing it all into deeper thinking before taking an action.
That's what it looks like. If you look at how that compute was actually used, the interaction scaling approach achieved superior results by spending smaller amounts of compute over many steps.
To get new info.
Right, to gain new information from the environment. While the other methods spent larger amounts of compute on complex reasoning within fewer steps, gaining fresh information through interaction often proved more valuable than just reprocessing existing information more deeply.
That just makes intuitive sense, doesn't it? In a dynamic world, getting new data from the environment beats just overthinking the old data.
It often does. But you mentioned a limitation with just prompting this check again behavior.
Yes. What was that?
Well, prompting isn't a perfect fix on its own. If you prompted the agent to recheck too many times, it could sometimes get confused or, in some cases, even start to hallucinate.
Hallucinate. How so?
Like essentially making up reasons to change a correct answer into an incorrect one. They saw a performance dip if they pushed it too far in certain task types, like map tasks.
I see.
So it highlights that while prompting proves the potential of interaction scaling, agents really need to be trained to effectively leverage longer interaction periods. You can't just keep telling them to check again indefinitely.
Right. Which brings us nicely to the next major part of the research. Moving beyond those simple prompts to actually training agents to use longer interaction horizons effectively. This is where they introduced their proposed method, TTI, which stands for test time interaction.
Exactly.
Yeah.
The idea is that just giving an agent more steps isn't enough. They need to learn how to use that extra time and opportunity well, how to explore, how to backtrack, how to recover from errors, how to dynamically plan over longer sequences of actions. It's a skill.
So did they just try standard online reinforcement learning first, just training agents with a fixed, long maximum number of steps?
I did try that. And they ran into some challenges.
Like what?
While training with a fixed short horizon, say 5 steps, teaches the agent the quickest path, but it often leads to overfitting. It fails if anything deviates even slightly from that learned path.
Okay, makes sense. What about a long horizon, like 20 steps?
That was unstable and much slower to train. In a long sequence of actions, it's really hard for the learning algorithm to figure out which specific actions taken early on were actually responsible for a good or bad outcome much later.
Right. That's the classic credit assignment problem in RL, isn't it? Hard to know which specific ingredient you added way back at the start made the final dish taste good or bad.
Exactly. The signal gets diluted, very noisy. So just fixing a long horizon didn't train the agent efficiently.
So that's where TTI comes in. What's the core idea?
It's actually quite elegant. Instead of training with a single fixed maximum number of steps, the agent's maximum allowed interaction length is gradually increased throughout the training process.
Like a curriculum. Start simple, then get harder.
Precisely. Start with shorter tasks or allowing fewer steps. Let the agent master basic actions in shorter sequences. Then, as training progresses, progressively allow it to take more steps, forcing it to learn more complex behaviors like exploration and recovery.
Did they look at how they increase the horizon, like add a few steps each time or multiply it?
They did. They experimented with different schedules additively, like adding 2 steps each phase,
Yeah.
and multiplicatively, like doubling the horizon. And they found that a multiplicative schedule actually worked significantly better.
Interesting. Why might that be?
Well, the thinking is it might expose the agent to those much longer horizons earlier in training, relatively speaking. This could help it avoid getting stuck just finding the absolute shortest paths and encourage it to learn those broader exploration strategies sooner.
Okay, so TTI is this training strategy that teaches agents how to effectively operate with an increasing budget of interaction steps. How did this curriculum approach actually perform when they scaled it up to larger, more realistic web browsing datasets?
They evaluated TTI on WebVoyager and the full WebArena benchmarks. And a really key part of their training setup involved generating a large number of synthetic tasks.
Using language models?
Yeah, using LLMs and an exploratory agent. And importantly, this data was generated using the same base model they were training a model called Gemma 312B.
Whoa, so it's kind of a self-improvement loop. The model helps create its own training material for interaction.
Exactly. That's a fascinating aspect of it.
So what were the results on those big benchmarks? Did TTI help?
It really did. TTI achieved state-of-the-art performance among open-source agents trained on open data on both WebVoyager and WebArena.
Okay, like what numbers are we talking?
On WebVoyager, for instance, it reached a 64.8% success rate. On WebArena, it got 26.1%. And this represented a pretty significant jump in performance compared to agents trained with fixed horizons or just zero-shot bit lines using that same Gemma-based model.
Those are strong results, especially showing the power of this training approach for agents built on open models and open data.
Definitely.
The paper does note, though, that proprietary models, presumably trained on vast amounts of private data, still achieve higher success rates on WebArena.
Yes, that performance gap is still there. It highlights ongoing challenges, perhaps related to the sheer complexity and diversity of real-world websites captured in WebArena compared to even large-scale synthetic data.
Sure.
But TTI clearly demonstrates a major step forward for training open, capable agents using this interaction scaling principle.
So let's dig into how TTI actually changes the agent's behavior then. What does it look like when an agent trained this way operates?
Well, if you look at the learning process, you see some clear trends emerging. As the TTI curriculum progresses and the maximum allowed steps increase, the agent's average trajectory length naturally goes up. They start taking more steps, basically.
Okay, that makes sense.
But crucially, you also see a significant rise in the use of exploratory and recovery actions, things like hitting the go back button or using an external search engine like Bing to find a solution.
So it's not just taking more steps randomly, it's using them strategically.
Exactly. The agent is actively using the environment to gather more information or to bounce back from issues it encounters.
And here's where it gets really interesting for me, tying back to that core tension we talked about. Did this increased interaction, taking more steps, come at the cost of thinking per step? Did it use more tokens per action?
Actually, no. They observed a learned trade-off. As the agent's trajectory length grew longer through TTI training, the amount of compute, the number of tokens used in per-step reasoning, actually tended to decrease compared to earlier in training.
Wow, seriously? So the agent automatically learned to spend less time deliberating within a single step because it knew it had more steps available later to explore, gather new information, or correct mistakes if needed.
That's the interpretation. It prioritized acting and getting feedback from the environment over deep single-step contemplation. It learned that often taking an action to get new information is a more efficient use of its resources than spending a lot of time thinking about limited information.
That's a fundamental shift in strategy learned automatically. Did they share any specific examples, like stories of agents succeeding or failing with TTI?
They did, yeah. They provide some great case studies. For strengths, they show effective exploration in complex tasks. There's an example where the agent is asked to find a specific kind of recipe. It tries one path, hits a pop-up that blocks it, but instead of just getting stuck, it uses its expanded interaction budget from the TTI training to backtrack, go back to the search results, and try a different recipe path. And it eventually succeeds.
That kind of flexible recovery behavior is exactly what you'd want.
Absolutely. That ability to backtrack and recover is vital for real-world tasks. They also saw strategic exploitation in simpler tasks.
Meaning?
Meaning, when the task was straightforward, The TTI agent was efficient. It took direct paths without unnecessary exploration, like quickly finding information on GitHub by navigating directly to the trending section. It learned to balance when to explore and when to just get the job done.
So it adapts its strategy based on the task complexity. That's pretty smart. What about the failure modes? Where did TTI-trained agents still struggle?
The case studies highlight some common issues too. One was an over-reliance on essentially resetting the task by going back to a search engine, like Bing, instead of trying more domain-specific recovery actions within the site they were on. If they hit a snag, their learned policy sometimes just defaulted to go back to search, rather than trying to navigate the issue locally on the site.
Treating BIM as the universal reset button?
Kind of, yeah. Another interesting failure mode was limited self-verification, especially right at the end, in the final step.
How so?
They describe an example where the agent successfully navigates to a GitHub project, finds the info, but then, despite seeing and perhaps even internally noting that the project was created in, say, 2021, not the required year of 2022,
Oh, no.
it still proceeds to submit it as the correct answer. The agent gathered the correct information through interaction, but failed that final self-check before completing the task.
Oof. That suggests that even with great interaction and information gathering, there's still a need for maybe better final verification or reasoning. Perhaps combining approaches is the answer.
The researchers briefly looked at that too, actually. They found that applying that simple check-again prompting mechanism we discussed earlier.
Right, the nudge.
Yeah, applying that on top of a TTI-trained agent could provide additional performance boosts. It acted as a sort of safety check.
So it helped?
It seemed particularly helpful earlier in the TTI training process, but it offered modest gains even for the fully trained agents. It suggests training for interaction and adding some inference time checks can be complementary.
Okay, that makes sense. So where does this research point next? What are the future directions?
Well, the paper points to several exciting avenues. One is extending this interaction scaling approach to other complex domains beyond just web navigation. Think robotics, or maybe automating tasks within desktop operating systems.
Anywhere an agent needs to act sequentially in a complex environment.
Exactly. Another big one is figuring out the optimal way to balance or trade off thinking more per step versus acting more across steps, not just at inference time, but maybe building that trade-off directly into the training.
Finding that sweet spot.
Right. And of course, continuing to explore more advanced reinforcement learning techniques that are better equipped to handle the challenges of learning over these very long sequences of actions, dealing with that credit assignment problem more effectively.
Okay. So for you, the listener, trying to make sense of how AI agents are evolving or maybe just grappling with the sheer amount of information out there, what's the big takeaway from this deep dive?
I think it's clear that building truly capable and adaptive AI agents isn't solely about increasing their internal processing power or how deeply they can reason before they act.
Right.
A critical, often more compute-efficient, and definitely complementary approach is enabling them to effectively interact with dynamic environments, to explore, gather new information, and adapt over time through sequential actions. And TTI provides a successful framework for training agents to actually harness this dimension.
It's a powerful reminder, really, that in dynamic real-world scenarios, intelligence often manifests not just through deep precomputation, but through that iterative process of doing, experiencing, and learning from the environment's feedback.
Indeed. And it leaves us with a thought to consider, doesn't it? If enabling interaction and information gathering is this crucial to agent capability, what are the broader implications for the future design of AI systems? It suggests it's not just about refining how they process information internally, but fundamentally maybe changing how they are allowed to experience and learn from the complex world around them.